Okay, so the example that I show you just now about the max and min of the direction derivatives is stated in this theorem in the notes. Okay, which is we can have the optimal direction property of the gradient. So which means that if you want to evaluate the maximum value of the direction derivative, so you have to put the positive magnitude of gradient f, and the direction is given by the gradient f itself. But if you want to get the minimum or the smallest value of the directional derivative, so you have to just put negative sign to the magnitude, and then the direction is you have just put negative sign of the gradient f. Okay, so in this case, if you are talking about you want to get the maximum slope or the maximum rate of change, or something related to the most increases the function f increases most rapidly, we have to just obtain the positive gradient f. Okay, if they ask about the value, then you just put the positive magnitude of the gradient f. But if the question is related to something minimum slope or the smallest or the decrease most rapidly, so we just put the opposite direction, which is just put negative. Okay. Okay, so the summary is provided here about the optimal property using the gradient f. Okay, so I'll give you another example which is related to the max or min of the directional derivatives. Here we have the example 26 and 27. So what is inside the example 26? So we are given the function t. So the function t in terms of x, y, and z. So we have 80 over 1 plus x squared plus 2y squared plus 3z squared. The temperature in degrees Celsius at the point P in terms of x, y, z. Find the greatest decrease. So what can you understand with the word greatest decrease? Something minimum, right? So the minimum value. So now we want to get the mean, something related to the smallest or minimum rate of change of the temperature at the point given. So in terms of direction, so the question here, find the greatest decrease. So in this case, it looks like they ask about the value itself. So using the gradient, we have because the function here t, so gradient t, so we have to put the negative. That is about the direction, but the value, so this is the direction, but the value itself we have to put negative of the magnitude of the gradient t. So this is the greatest decrease of the temperature. Okay, so in this case, what is the gradient t? Gradient t is you have tx, ty, and tz. Okay, so because firstly we have to find the gradient t first. So we have to evaluate. We have to find the tx. Differentiate t with respect to x. So let's say here I rewrite the t here to be 80 1 plus x squared plus 2y squared plus 3z squared to the power of minus 1. So when I differentiate that with respect to x, so negative 80, and then I have 1 plus x squared plus 2y squared 3z square minus 2, and then differentiate the inner function here with respect to x, so I have 2x. When I simplify, I will get negative x over 1 plus x squared plus 2y squared plus 3z squared to the power of 2. Okay, and similarly for ty, I will get negative 80 multiplied by 4y divided by 1 plus x squared plus 2y squared plus 3z squared then will give me negative 320y over 1 plus x squared plus 2y squared plus 3z squared. Okay, and tz, so negative 80 and then 6z over 1 plus x squared plus 2y squared 3z squared. Then this will give me 480 z over 1 plus x squared 2y squared 3z squared. Okay, so that is, then we have to, because they ask us to evaluate at the point 112, then we have to evaluate. So the point is at 1, 1 minus 2. So we have to replace. Okay. So we have 1 over 1 plus 1 plus 2 plus 12 square. So we will get 16 square. Okay, so when you evaluate that, so that is the result. So here we have negative 5 over 8 minus 5 over 4 and 15 over 4. So in terms of direction, so direction of the minimum directional derivatives is given by negative gradient t. So we will get 5 over 8, 5 over 4, negative 15 over 4. Okay, but the magnitude, so then the value, the greatest decrease, so the greatest decrease is given by negative of the magnitude. So the magnitude is 5 over 8 square plus 5 over 4 square plus 15 over 4 square. Then this will give you, okay, so the answer in I give 5 decimal places is minus 4. So that is the minimum rate of change for the given temperature at the specific 0.11 minus 2. Okay, so now look at the example 27. So example 27, so you are given a function in terms of x, y, z, which is you have x minus y and then y plus z. So find the directional derivatives. So find the directional derivative of f at the point 1, 3, 1. So gradient f dot u. So the direction vector given is not in the vector form, so we have to find it. So the vector v is given by 2 minus 1, 2. So the unit vector of vector v is 2 minus 1, 2 divided by 4 plus 1 plus 4. So you have 2 over 3 minus 1 over 3 and 2 over 3. Okay, so that is your unit vector. And you have to find the fx and fy. So in order to get that, here I just expand. So I have xy plus xz minus y squared minus yz. Okay, and then in this we have to obtain the fx, fy, fz dot with the u1, u2 and u3. Okay, so fx u1 plus fy u2 plus fz u3. Okay, so fx, find fx. So you have y plus z, and then fy you have x minus. Okay, so fy, so x minus 2y minus z. Okay, and fz you have x minus y. Then because of we know we should evaluate at the point 1, 3, 1. So y plus z we got 4, and then this one, so x 1, 2, 3 we got 6, so we got minus 6, and x minus y we got minus 2. Then the gradient f here dot with the unit vector. So we just replace fx. Fx is 4 and u1 is 2 over 3. And fy is minus 6 minus 1 over 3 and then minus 2 and 2 over 3. So we have 8 over 3 plus 6 over 3 minus 4 over 3. So we will get 10 over 3. So that is the directional derivatives for the specific vector given. Okay, so that is the first question from example 27. Next, determine the direction at the point given in which the rate of change is maximum and find its maximum value. So the second one is asking for the maximum rate of change. So now to answer the next question, we want to find out the maximum rate of change. So we want to find out the direction. So the formula to get the direction is the gradient f. Okay, and then the value is the magnitude of the gradient. This is value, the maximum value. So now we obtain the direction, which is it should be vector form, where it is fx, fy and fz. So since we already compute the fx, fy, fz for the point given, so we can just put the value 4 minus 6 minus 2, and the magnitude, where the maximum value is the square root of 16 plus 36 plus 4. Then this will give you square root of 56. Okay, so that is the direction. So the direction is the gradient f itself, which is vector 4 minus 6 minus 2, and the maximum value, just magnitude of the gradient f. That's it. Okay, so that is the example which are related to the optimal property of the gradient.